This is Hydraulic Engineering for the 23rd of January, class number 4 of the semester, and we'll begin with a couple of announcements. First of all, this class is online. In case you hadn't noticed already, we are not in person. We are having this class online, so hopefully you're enjoying the SAME ASCE Winter Technical Conference today. The next homework assignment number 2, is due on Tuesday, the 28th of January. I'm going to go over some tips for that assignment here in just a minute, but that assignment's due in class, and it's the homework problems that are identified on the screen there and also in our course schedule. Also mentioning the course schedule, the class on Thursday, as indicated by the schedule, class number 6 is going to be online for Thursday the 30th of January. So that's a week from today being the 23rd of January. We're going to be working on, in this lecture, the continuation of the pipe diameter sizing example that we didn't get quite through last time in class. And then we're going to move on to a comparison of some of the different empirical resistance equations for characterizing head loss due to pipe friction. Before we get into that, here are a couple of homework tips that I'd like to offer you as maybe a Kickstarter to that assignment that's due on Tuesday. First of all, for problem 8.1, they say in that problem that the pipe is smooth, and you can't necessarily know the F value just from the fact that they've said that the pipe is smooth, but what you can do to find the F value is if the flow conditions are laminar, and I'm just saying if, I'm not saying that they are, but if they are laminar, remember that there's a very easy way of calculating the F value, and that's 64 divided by the Reynolds number. So hopefully that might come in useful for you. Problem 8.4, I'll remind you that the text is a wonderful reference of all sorts of information. Since we didn't go through some of the earlier chapters, though, you may not be acquainted with where the fluid properties can be found, and those are found on page 33. Table 2.1 has the physical properties of water in SI units, and table 2.2 has the physical properties of water in British gravitational units. So you can find what you need there in that table's property. And I'll also ask that on problem 8.4 you use the Colebrook equation to find F. It's important you get a couple of examples of going all out, the full computational, the difficult implicit equation with the Colebrook equation. So use 8.4 as an example, as an opportunity to find the F value by Colebrook equation. However, on problem 8.5 you can use the Jane equation. Remember, the Jane equation is the easier of the two methods. It's the approach that allows you to calculate F in an explicit manner. The F value isn't on both sides of the equation in the Jane, but rather in the Jane equation you're using the equivalent sand roughness of the material, you're using the pipe diameter, the flow conditions, and so on to find the F value. In problem 8.17, they mention a differential manometer. There isn't a picture with that problem, but they mention it's a differential manometer and it's a horizontal pipe. I'll take you back to fluid mechanics, and in fluid mechanics we learned about differential manometers, and we learned that what they measure is the difference in piezometric pressure. P sub z means piezometric pressure, and piezometric pressure is pressure plus gamma z. In this case, since it's a horizontal pipe, though, really what the differential manometer is measuring for this horizontal pipe is the change in pressure between location 1 and location 2. So you need to take into account the difference in the unit weights between the two fluids. The manometer fluid, which in this case is mercury, having a specific gravity of 13.56, allows you to calculate the unit weight of mercury, because you remember that specific gravity is the ratio of that fluid's unit weight relative to the unit weight of water. And then also the fluid that's flowing through the pipe, in this case, is water. So the delta H they give you in that problem, you'll need to find the difference in the unit weights, and from that you'll find the delta P. And if the pipe is horizontal, then you can find the head loss between 2 points. And the only reason why there's a difference in pressure in this example is that head loss is occurring, frictional losses due to flow through the pipe. So that delta P can be used to calculate the H sub F. As long as you divide by the unit weight of the fluid flowing through the pipe, You can get the h sub f from that. And then in the Darcy-Weisbach equation, of course, that is the h sub f is the whole point of the Darcy-Weisbach equation. So if you put that known value for h sub f into the Darcy-Weisbach equation, you can back calculate for the f value that's making that entire problem true. That's the essence of problem 8.17. In problem 8.26, I wanted to remind you that the unit weight of water is going to be in terms of pounds force per cubic foot. The units are a little bit strange when you start working in British gravitational units. The definition of horsepower, HP, horsepower, is you can calculate horsepower by the unit weight of the fluid, in this case water. The flow rate has to be in terms of cubic feet per second. So I think you'll need to make a conversion in that problem from the given flow rate into cubic feet per second, multiplied by the pump head. So in this problem, if they tell you the horsepower available, you'll know the unit weight and the flow rate. You can find out how much pump head is being added to the system, so that then you can find the head loss and the energy equation. Since you know how much pump head is being added and you know all the other terms in the energy equation, you can use the iteration approach that was demonstrated in the last part of the last lecture and in class today, how to find D. That approach of starting with a guess F value and finding out what diameter that would give you and then correcting. We're going to go through that example again in this lecture, so that you'll apply that approach to solve the rest of problem 8.26 once you have calculated the head loss. And finally, for problem 8.28, I wanted to mention that there's a range of values that can be used for riveted steel. If you turn in your text to table 8.2, which is on page 231, you'll see that riveted steel has a C value that goes, riveted steel coated goes from 90 to 110, and riveted steel welded goes from 100 to 140. So just for purposes of standardization, let's all use the same C value for the Hazen-Williams coefficient of 110 on that problem. Okay, so this is the example we didn't quite finish last time in class. We have a pipe length of 40 meters from some origin. Maybe this is a tank or a larger pipeline. Here we've got a lateral pipe, 40 meters long, and it's made out of cast iron, which we know the equivalent sand roughness is 0.26 millimeters, and we want to get 300 liters per second through there. And the head loss that's available is 45 meters. That's just based on what the pressure in this pipe is. That's the driving force that's going to be getting the water through the pipe. So if we've got 45 meters of head to push the water through the pipe, and we need to get 300 liters per second through there, how big should the diameter be? That's the essence of what we're trying to do in this example. So just as a refresher on what this method entails, we're going to begin with some assumed F value. Because remember, the initial conundrum that we face is we don't know what the diameter should be until we know the F value, but we don't know the F value until we know the flow rate, the flow velocity. And we don't know the flow velocity until we know the roughness, and we don't know the roughness until we know the F value. So it's this circular logic that we have to jump into the circle at some point just by making an assumption. You know, pick an F value and hopefully improve your guess along the way. So our first thing will be to assume some guess value of F, and then by typing the equation into Excel, we'll get what the corresponding D is for that guess F value. We'll find out if that's the diameter, then what's going to be the flow velocity, therefore what will be the Reynolds number, and we already know the K sub S, but what would be the relative roughness, the K sub S to D, if we have this D that depends on our assumed F. And then we're going to use either the Jane equation or the Colebrook equation. Since I'm going to be doing it in a spreadsheet and I'd like for it to be relatively automated, I'll use the Jane equation, and it's generally good enough for our purposes, to find a new F based on these flow conditions. And then we'll compare what was our initial guess F value compared to this newly calculated F. And if they are perfectly equal, then that works out great for us. If they're not perfectly equal, that means our solution hasn't converged and we need to iterate. We need to repeat again, starting with some new f. And this time we won't pick some assumed f value from thin air. We'll start the process over again with this newly calculated f value. And we'll continue to repeat that cycle until the difference between our starting f and our final f in each cycle is very small. And that small difference tells us that we have converged. Alright, so let's get into that example. I handed out a spreadsheet last time, the solution of this example, but I wanted to record it so that you can go through it yourself, and so you can key in all of the areas where we need to put in known values and so on. For example, we know the flow rate here is 0.3 cubic meters per second. Our equivalent sand roughness for this cast iron pipe is 0.26 millimeters. So if I want that in terms of meters, I can do 0.26 millimeters divided by 1,000 to get it in terms of meters. The pipe length is 40 meters, G is 9.81. The head loss due to pipe friction is 45 meters, and our kinematic viscosity of water, 1 E minus 6. That means 10 to the negative 6th meters squared per second. My initial guess F value, just to show how good this method is, I'll start with a value at the very low end. Ordinarily, I'd get it converged faster if I picked sort of a midpoint F value. It would hone in on the correct answer more quickly if I started with a midpoint value of maybe 0.02. But I'll start with 0.008, which is at the bottom of the range of typical F values. And so now what is the diameter based on that F value that I just assumed? I have to type in the equation here. So I'll do that. I'll type in the equation. It is 8 times the length. Anchor that, because I want to always be looking at that same length when I apply the equation into other places, times the flow rate squared divided by H sub F, anchor that, divided by times G times pi squared, so pi parentheses, that gives me pi, and now I need to square it. Close that, and then I need to multiply by f again. I guess I should have maybe just put it in the original part of the expression, but it doesn't matter, I can do it here. Times f. I'm not going to anchor that, because when I copy and paste this formula somewhere else, I don't want to have to type this in every time I use this formula. I want to be able to paste it, but I don't want it to be looking at the original f every time. So I'll close that out. I think I got too many there, didn't I? Let's see, just this one and one, that did it. Yeah, okay, and now to the 1/5 power. Alright, so here's the diameter that there would be if this is the f value. And it's very useful that I've typed in this formula. I'll be able to just do copy and paste somewhere else later on when I'm ready to find the D again. I won't have to type that in once again. So determine the flow conditions. You know, the flow rate is already known. I'm just going to base that on the original flow rate. The cross-sectional area is going to be pi times d squared divided by 4. And that gives me the area, 0.0153. And now velocity we know is q divided by a. So this is the flow velocity through the pipe if this is the diameter. So if that's our diameter, then this is the flow velocity, and now I'll use the Reynolds number formula to find what's the Reynolds number. So it's going to be the velocity times the diameter divided by the kinematic viscosity of water. And I'll anchor that so that I always come back up to the same cell, regardless of when I copy and paste. So we've got a Reynolds number there. And so now what's this new calculated F value based on the Jane equation? Let me type in the Jane equation, 1.325 divided by, I'll make that even bigger, hopefully you can see it. You know, this is a high definition recording, so you should be able to, in YouTube, change it so that it displays in its full resolution. Equals 1.325 divided by the logarithm of the k sub s value, this, I'm going to anchor it, divided by 3.7. And remember, I told you that I sometimes do this funny trick where instead of multiplying in the denominator, I just divide again. So divide by this d that we're working with in this step, plus, now I'm working on this side of the term, 5.74 divided by the Reynolds number to the power of 0.9. And then I need to square that at the end, consistent with this exponent. Okay? So I get some new F value. So what's the percent difference between my initial F value and the final one? So I'll do this minus that divided by, oh, I need to put in parentheses there. So the difference divided by the original times 100. Big difference there. I guess we should say that maybe the newly calculated one will assume that's true instead of the original. So this is, we know it's better. This is always going to be improving our guess. So we'll say that the true value is the newly calculated one. So that takes our percent error a little bit lower, but our initial guess was still too small. So that's why the negative value there, negative 65% different. That's not good enough. We have to repeat. And so instead of just assuming an F value from thin air, you know, I'm not going to go from 0.008 to 0.009. I can do better than that. I'm going to say, well, let's use this as my value from above. And now to calculate D based on an assumed F, I don't have to type in the equation again. I'm just going to highlight this cell where I've got the D calculated. And remember, I was really careful to put in anchoring for all of these terms. You can see where it's anchoring to, except for the one term I didn't anchor was the F value, because I want it to take a look at the new F value when I copy and paste that equation. So I'm going to right click, copy, go down here, right click, paste, and what I want to paste is the equation, the formula, and it calculates the new the new diameter based on that F value that we got at the end of the first iteration. So the flow conditions, I'm going to just copy all of this. I'm going to, instead of doing right-click copy, I'm going to use the shortcut key, which is Control-C, and then I'm going to highlight that cell and do Control-V. That didn't work. There must be an extra space in there somewhere. That's what happens. If you put in an extra space, then the direct copy and paste doesn't quite work. So I'll just do this. The flow rate is there, and the formula for area, and the formula for velocity, Control-C. Oh, I guess it was already okay. It was maybe just the Q value that was messed up. So let's just take a look at that formula. First of all, to look that it pasted okay for when we were calculating the D, it's looking at all of the constants up at the original, but it's looking at the new F value in this second iteration. And the same thing is true with copying and pasting those formulas for the area and velocity. Everything's fine. Reynolds number, we can do the same thing here. Control-C, Control-V, we get the new Reynolds number. And so the new F value, this is the Jane equation, so I'm going to copy Control-C and Control-V, and that gives me a new F value at the end of iteration 2. So we're gradually getting better. If I copy and paste that percent difference formula, now my percent difference is only 5.43% different. So again, I'm going to assume an F value. I'll assume the output of the second iteration, and then everything else, I'm going to just highlight this whole thing. Instead of copying and pasting it piecemeal, let's just copy and paste the whole thing. So I'm going to paste that below the first line. So now Control V. For some reason the flow rate's not working, but that's easy enough to say the flow rate. Maybe I need to anchor that. Alright. So the percent difference is getting really small, isn't it? 0.26% difference. So the input F value was 0.0219. The output was 0.022. Let's do it again. It's easy enough. I'm going to highlight all of this. Control C to copy. Control V. Now I need to have it look at the output value of that F. But everything else, it does all by itself, and the percent difference is so small that the solution has converged. And we're excited about that, thus the exclamation points. And you can see that the F value coming out of that iteration is the same as the F value coming in, which means now we know the correct F value and we know the correct diameter. This is the answer to our question: how big should the pipe be in order for the flow to go through this 40-meter pipe length with the head loss available at driving force of 45 meters. It should be a diameter of 0.1707 meters. I don't know that they make pipe exactly that size, so we'd probably want to step it up. We'd want to go to the next biggest pipe diameter that is available. Maybe they have a 0.2 meter diameter pipe, maybe 0.25 if they're working in certain increments, but you want it to be a little bit bigger than needed rather than too small. Alright, so that is that's the approach for iterating to find the pipe diameter required. And as I mentioned at the beginning of this lecture, you'll need to apply that approach for one of the homework problems. I showed you this expression in class on Tuesday, and it's the so-called easy approach that avoids the need for iteration. It's an empirical expression that says usually if you're within a certain Reynolds number range and for a certain range of relative roughnesses, the diameter can be predicted within 5% by using this approach. And just to compare what we've done in the previous example, this iteration example that we just did, to if you're going to apply the this formula would tell you that the pipe diameter needed, this explicit approach, is 0.175. So if you can pop it into your calculator if you like, it would say 0.175. So that's pretty close, but this is the truth in how big it needs to be.
There are three methods that we can compare for calculating frictional losses in pipelines. The first of them, the Darcy-Weisbach equation, is the most accurate because the friction factor that's used in this formula, the F value, varies as a function of flow conditions, the liquid that's being transported in the pipeline, and also the pipeline characteristics itself. So therefore you could say that it's the most flexible of the three equations that we're going to look at here today. The disadvantage of the Darcy-Weisbach equation, of course, is that in having all of this flexibility and specificity for the actual flow conditions that are being observed, that means that you have to calculate an F value, whereas some of the other empirical equations have a friction factor that doesn't change as a function of flow conditions. So it can be a little bit more time intensive, but generally I think that the accuracy is worth the investment. By comparison, the Hazen-Williams equation is easier to use than the Darcy-Weisbach equation because the C value is constant over a range of flow rates. Now, as a consequence of that, the Hazen-Williams equation has limited conditions under which it's applicable. It's only used for water. It can't be used for other fluids flowing through the pipeline. And there's only a range of pipe diameters that it's valid for, from 50 to 1850 millimeters, which means, and might explain that, remember last semester when we were applying the Hazen-Williams equation, we saw some strange behavior. Part of the reason that might have been is because the pipe diameters were smaller than that which the Hazen-Williams equation is actually intended. Another restriction is that the water is assumed to be at 16 degrees Celsius when you're applying the Hazen-Williams equation, and the reason for that assumption is that it fixes the kinematic viscosity of the liquid so that that's not variable. Remember that that is variable in the Darcy-Weisbach equation. When you calculate F, part of what goes into finding the F value is the Reynolds number for a certain flow condition, and the Reynolds number is a function of the kinematic viscosity of the liquid. So it's definitely easier to use the Hazen-Williams equation than the Darcy-Weisbach equation because the friction factor, not only does it not have to be calculated, but it's not an implicit equation like the Colebrook is. It can be expressed in two different ways. One form of expressing the Hazen-Williams equation is to find an unknown velocity for a certain pipe roughness that's known, that depends on the material that's being used to convey the flow. Based on the flow geometry, the hydraulic radius here, of course, is the area divided by the wetted perimeter, and the slope of the energy grade line, S sub F. And the energy grade line slope is defined as the head loss through the pipe between 2 points, divided by a certain length over which the 2 points are separated. So you can find the slope of the energy grade line if you know, for example, the pressure drop over a certain length of pipe. Another way of looking at the Hazen-Williams equation is if you know a known velocity of flow through a pipeline and the length and diameter and roughness of that pipe, then you can use the Hazen-Williams equation to calculate how much energy is going to be lost due to pipe friction through that conduit. And of course, in British gravitational units, the equations are a little bit different because of the conversion factors between meters and feet and so on. So the BG version of the Hazen-Williams equation has to be solved separately. The exponents are the same, but the coefficient at the beginning of the equation is different. A third method, which is not often applied for closed conduit, but can, is Mannings equation. More commonly, Mannings equation is used for open channel situations. The roughness factor here in Mannings equation is an N value. And you'll notice that in contrast to the Hazen-Williams equation, where the roughness factor here in finding the flow velocity is in the numerator of the equation, in calculating the flow velocity according to Mannings equation, it's in the denominator. And what that means is that a pipe that is smooth, when you're solving for the flow velocity with Mannings equation, you're going to have a small n value for a smooth pipe. Whereas in contrast, a big C value corresponds to a smooth pipe because a smooth pipe would give you a faster velocity. And we'll look at a table of comparing different materials for both their C values and their N values. And again, there's a difference between the SI version and the BG version of Mannings equation. The difference here being the correction factor of 1.485 for the British gravitational system. And again, the slope of the energy grade line, S sub F, is defined as how much energy is lost due to pipe friction over a certain pipe length, L. Now, to compare those roughness coefficients, you can see that in a new pipe compared to an old pipe, for example, the typical C value for a new cast iron or ductile iron pipe would be 130 because it's more smooth than an old pipe which maybe has mineral accumulation on the inside of it, or it might be corroding due to rust. And so it would have a lower C value, and therefore for the certain driving force of the energy loss is going to have a lower velocity. In contrast to that, the N values are on the low side for smooth pipe and on the high side for rough pipe. And so there's a range of values for each of these different materials, and a typical value that you could use if you don't want to make an assumption of it being on the rough side or the smooth side. What we'll do next is take a look at an example where we're comparing these three different methods to find the energy loss due to pipe friction over a 500-meter length of pipe, where we know that the flow velocity is 1 meter per second and that the diameter of pipe is 150 millimeters. So what we're going to do in this comparison is find out how much energy loss does the Hazen-Williams equation predict there will be, how much does Mannings' equation predict that there will be, and Darcy-Weisbach, which we assume is the most accurate. In this example, we're going to be comparing the head loss that is calculated according to three different methods for the same situation. In this example, we have water flowing through a pipe that has a diameter of 0.150 meters. The velocity going through the pipe is 1 meter per second, and the C sub h value, the Hazen-Williams roughness coefficient, is 130. That's given. The Mannings N is 0.013. And for Darcy-Weisbach, we can know the equivalent sand roughness, K sub s, or epsilon. That is 0.26 millimeters. And we get that information from table 3.1. So what we're going to do is, for a length of pipe of 500 meters, try and find how much head loss there is according to each of the three different methods. The first of these methods that we'll calculate is the Hazen-Williams. There are a couple of different forms of expressing the Hazen-Williams equation, and the one that we're going to use is how you can calculate the head loss due to pipe friction directly if you know the length parameter, the diameter, the velocity, and the roughness coefficient. You'll notice that there are some pretty bizarre empirical coefficients that we use in the exponents there. And this is an empirical equation that's been developed just observing head loss data for a variety of different pipes. Remember that there are restrictions on the cases where you can use the Hazen-Williams equation. It's not always valid. It's restricted just to water, technically for a certain temperature and for a limited range of flow velocities. But besides those restrictions, it generally gives a pretty good result. So we will substitute in the given information that we have 500 meters, and the diameter of the pipe is 0.150 meters to the 1.17 power. And here the flow velocity that's known is 1 meter per second, and the roughness coefficient is 130 to the power of 1.85. If we put that into a calculator, we'll get that this term is equal to 31,385. This expression, 1.228 times 10 to the minus 4. I usually break it up into pieces like that just so I can double check my work. Never rely on the first set of calculations. We get that the head loss due to pipe friction is 3.85 meters according to this approach. Now let me emphasize that, remember, there are two different sources of head loss. There's head loss due to pipe friction and head loss due to local losses, or sometimes called minor losses. This is just for pipe friction. There might also be some fittings along the way that could reduce energy due to local losses, and this would not account for those. And next we'll move on to considering how much energy is lost according to the Mannings expression. Now, Manning is more commonly used in open channel flow, but technically it can be applied to closed conduit flow, and let's see how accurate it is when we do that. The Mannings equation, when we express it in terms of the head loss, which is not the typical way that it's expressed. Typically it's expressed in terms of flow rate, but we can rearrange it algebraically to solve for head loss. from that, if we substitute in the known value, 6.35, the N here, for a typical ductile iron pipe, we're going to use 0.013, and squared. 500 is the length. Our velocity is 1 meter per second, squared. And the diameter is 0.150 meters to the 4/3 power. Okay, so that goes to 0.5366 and 7.97 times 10 to the minus 2, and we get 6.73 meters of head loss according to the Mannings equation. So that's quite a bit more than we got with the Hazen-Williams equation. If we were calculating a percent error, then we can assume that the Hazen-Williams equation will be more accurate for closed conduit flow than Mannings. Darcy-Weisbach is the best of them all, however, and the reason why is that the friction expression, the F value, is sensitive to flow conditions. Instead of using a constant C value or a constant N, we have to calculate F based on the specific flow conditions that we're experiencing. And the way to first of all apply the Darcy-Weisbach equation for our K sub S that we know of 0.26 millimeters is we have to calculate the Reynolds number, because we're going to use that in the Jane equation, the Colebrook equation, or with a Moody diagram. So the Reynolds number here is the velocity times diameter divided by the kinematic viscosity. The velocity is 1 meter per second. The diameter is 0.15 meters. And the kinematic viscosity of water under typical conditions where we haven't been specified some other temperature, 1 times 10 to the minus 6 meters squared per second. So we can pop that into the calculator and get 1.5 times 10 to the 5th. And of course Reynolds number is unitless. And if we put that into the Jane equation, then we can find the F value is 1.325 divided by the natural log of K sub S divided by 3.7 times D plus 5.74 divided by the Reynolds number to the 0.9, and all of that is squared. Remember, the Jane equation gives us a pretty accurate estimate of the F value. If we wanted to go all the way and have hyper accuracy over any number of range of flow conditions, we'd use the Colebrook equation, but under most circumstances Jane will work just fine. So we'll substitute in the known values here. We've got 1.325 divided by the logarithm of the sand roughness of the pipe, 0.26 millimeters, divided by 3.7 times the diameter of the pipe, and we have to have that diameter expressed in terms of millimeters for the dimensions to be consistent in this term of the expression. 5.74 divided by 1.5 times 10 to the 5th is our Reynolds number to the 0.9 power. All of that is squared. So we get from the Jane equation that the F value is 0.0240. And so that's the roughness value for these specific flow conditions, meaning for this specific pipe diameter, for this flow velocity, and for the temperature of the water, which factors into the kinematic viscosity. Neither the Mannings equation nor the Hazen-Williams expression takes any of those factors into account in generating roughness values. So now if we want to calculate the head loss due to pipe friction, we put that into the Darcy-Weisbach equation, which is H sub F is FL V squared divided by D2G. And we know our F value that we've just calculated is 0.0240. The pipe length is 500 meters, and the velocity 1 meter per second. Square that term, divided by the pipe diameter, this time in meters to be dimensionally accurate with the rest, times 2G. Alright, and we do all those calculations, get 4.08 meters. And we can know with pretty good confidence that Darcy-Weisbach equation will give us the most accurate expression of the head loss due to pipe friction. So from that we know that the Hazen-Williams equation in this instance was too low, and that the Mannings equation was too high, but the Darcy-Weisbach equation was just right. Our final example today will be similar to one of your homework problems. What we're trying to do is find out what pipe diameter is needed to lift water from a lower reservoir up to a higher reservoir, where we have an 800-foot section of pipe, and the elevation difference between the two is 35 feet. So we have a pump that we know is a 10 horsepower pump, and we can use the horsepower equation to convert that 10 horsepower into pump head that's being added. And then we're going to find out, if however much pump head is being added, some of that goes to lifting at the delta Z, the rest of it goes into pipe friction. If we want to achieve 1.5 cubic feet per second, then what pipe diameter is needed? So this problem can be solved pretty easily using Excel. And I've started setting that up in Excel. What we'll begin with is that we know the pipe diameter is unknown, but a lot of the other information is already given. We know, for example, that the pump head is 10. Horsepower is how much energy the pump is, and we know for cast iron it's 0.00085 feet is the equivalent roughness, and the unit weight of water is 62.37 pounds of force per cubic foot. From the table we can find that the kinematic viscosity of water is 1.22 times 10 to the minus fifth feet squared per second. The flow rate we want to achieve is 1.5 CFS, and the pump head we're going to calculate using this formula, rearranged to solve for H sub P. And so that is 550 times the 10 horsepower divided by the unit weight of water divided by Q. And that tells us that we're adding 58.79 feet. And that's good. If we were adding less than 35, then the flow rate would be 0. So you have to at least add 35 feet of head, or else you can't get the water from this tank to the next. And so how much of that 58.79 that the pump is adding is left over for pipe friction? Well, it's going to be the original amount minus their 35 feet of elevation change. And basically what I'm doing here is I'm just solving the energy equation, where Z1 and Z2, the difference between Z1 and Z2 is 35 feet, and the pressure head at both of the origin and location is 0. So H sub F is just going to be the difference between the elevation and the pump head. So what's left over is 23.79 feet of head. G in traditional units is 32.2 feet per second squared, and this pipeline is 800 feet long. Alright, what I'm going to do in the next step is I'm going to just guess an F value. That's what we often have to do in these pipe design situations, is guess an F value. I'm going to calculate the diameter of the pipe that corresponds to that using this formula. I'm going to calculate the cross-sectional area based on that pipe diameter, and the velocity that's flowing of the water flowing through the pipe based on this cross-sectional area, and the known flow rate that we want to achieve of 1.5 cubic feet per second. And then finally calculate a Reynolds number based on all of that. And Reynolds number, of course, is unitless. Okay. So if we guess an initial starting F value of 0.01, then the diameter of the pipe, I'm going to use this formula now, is 8 times the pipe length, and I'm going to anchor that since it's a constant, times the Q value, also anchored, squared times f. I'm not going to anchor f because I'd like to copy and paste this formula for use later on since I have to iterate. The f is going to be changing from step to step. Divided by, now I'm going to use that thing where I just divide by a bunch of times instead of putting in parentheses. Divide by h sub f, divide by g, divide by pi squared. And all of that is to the 1/5 power. Be sure that you put parentheses around the 1/5. And that tells me what diameter is needed if this was the f value. Okay, now if I had that diameter, then the cross-sectional area would be pi times d squared divided by 4. Now I've got the cross-sectional area. The velocity would be q divided by a. And I want to anchor that q reference since it's always going to be the same flow rate, even when I paste this formula into other cells. And now the Reynolds number can be calculated with the velocity times the diameter divided by the kinematic viscosity. And that is, the kinematic viscosity is a constant. Okay. So what I've done now is with calculating a Reynolds number, I can calculate an actual f value. So this was just an initial guess. So now I'm going to go through this process again. For the second time around, I'm not going to have just a guess out of thin air. I'm going to calculate the f value according to the Jane equation. 1.325 divided by the logarithm of k sub s divided by 3.7. Okay, so k sub s divided by, I need to anchor that, divided by 3.7 divided by d. And the d I'm going to use is the d from the previous step. Now plus, I'm doing the right-hand side of the Jane equation, 5.74 divided by the Reynolds number to the 0.9 power. And all of that is squared. So now I have a better guess of the f value than that one that was just taken out of thin air. And the d, remember I typed in the formula for d previously? Well, since all of those cell references are anchored, if I copy and paste, it will look for the f value immediately above the cell that I pasted into. And the rest of the time, it'll be looking at the constants that were anchored up here. So all I have to do for the formula for d is I can do Control-C, which is copy, and Control-V, which is paste. And then if I highlight that cell, you can see from the formula, it's looking up here for all of the constants, and then for this new diameter, it's based on the newly guessed f value. And so I have a new diameter. Originally, in the first iteration, it thought it should be 0.453 feet, but in this new iteration, it's saying it needs to be a little bit larger. Likewise, I can have the area, velocity, and Reynolds number. I can just copy all of them, because what I'm really copying isn't the numbers, I'm copying the formula that I typed in before. So if I Control-C to copy and Control-V to paste, I have a newly updated guess of what the diameter is needed and what the cross-sectional area be and what the velocity will be. So now at this point, since everything is relative formulas, I can Control-C the entire iteration at once. And so I don't have to type things in again. And let's look at how things are changing. In the first iteration, we went from 0.45 to 0.54 feet in diameter. And the next step, the change is much smaller. There was a pretty dramatic change in diameter in the first, from iteration 1 to iteration 2. And now there's a relatively small change in diameter. What that means is that the solution is converging. We're getting close to the right answer. We'll know we're at the right answer when the velocity isn't changing anymore from iteration to iteration, when the f value is stabilized, and when the diameter doesn't change anymore. So it's easy to pump out these extra iterations. You just do Control-C, Control-V. You can do it several times, and you'll notice that the diameter is achieved convergence. The F value has converged. And that tells us that the diameter that's needed, this is our answer for the diameter that's needed, because nothing's changing. We don't have to control C, control V any longer because the solution is converged. So the question that was originally posed by this example is what pipe diameter is needed for the situation where a 10 horsepower pump, and when we know it was a 10 horsepower pump with a certain flow rate and a certain unit weight, that allowed us to calculate the pump head H sub P, which we substituted into the energy equation along with the delta Z, and that told us how much H sub F is allowable, how much energy loss there's going to be. And it was with the energy loss calculation, H sub F, that we were able to determine what the diameter of the pipe that's required is. And so our final answer here, 0.535 feet, is the diameter of the pipe that's required.